Hi everyone, I hope you're doing well. This is lesson 3 in our first unit. I just want to start this one by talking about something we kind of discussed a little bit last class. And that's this kind of situation where you have how many arrangements are there for 3 students in a line at the front of the class. And this is easy, I think, most easily thought of when you think of these as placements. And so it's 3 people in a line. And so there are 3 places for them. What that does is gives us 3 stages. If you think of the tree diagram, 3 stages in this organization of arrangements. For the first placement, we have 3 options, right? We have 3 people, we got 3 options. So we're going to put one of the 3 there. But what this is so important to understand this is really the number of options. In fact, all of the stages, you're talking about the number of options in each stage. In this situation, if I put one person there inherently is no repetition. I can't duplicate the person. So the next stage or the next person in line, I have 1 less. So that goes to 2. And then the next person in the line, I have 1 less than that because I put someone in the second place and I'm down to 1. And so I end up with 6. This will always be the case for when you have things that can't be repeated, as well as the fact that they are different from each other. So for example, in the next one, it says how many ways are there for arranging these letters? These are all different letters, and we're going to assume no repetition. And so similarly, it's just a 3 times 2 times 1. And if we had larger numbers, for example, if we're arranging different blocks, again, because they're all different, that fits this case. If we were arranging them in a line, you'd have 4 times 3 times 2 times 1, or 24 different arrangements. And you could think of this in a tree diagram. It just starts to get really, really big, especially when you get up to this kind of situation with 5. So now I've got 5 places. And you end up with a bigger number, quite a bit bigger, so 5 times the previous one. And this we can start to generalize with the notation, which we briefly talked about. But this is a factorial. And a factorial is a mathematical procedure. And so this looks like you're screaming the number 5, this exclamation point, but it represents factorial. And what it represents is that you are taking that number and then timesing it by 1 less than that number, and then timesing it by 1 less than that number, and so on until you get to times 2 times 1, or times 1 if you want to think of it that way. It will never go to negatives, or else it just doesn't make sense. If you started multiplying by 0, you wouldn't have any results. So this one, 6 blocks, you can think of it as 6 factorial. And you could just write that. You don't need to expand it all the time, and your calculator will do it for you. But really this is, I will write it this time, but this is this, until I get to down to 1 here, and you get an answer which is 720. I'm going to write this out a bit longer way because we're going to generalize this, and factorials are sometimes used in other situations within math, and this is the course where you kind of learn factorials. So I'm going to look at it in general like this. If I have 6 factorial, whatever the number is before the factorial will always be the first term. So I have a 6. And then I multiply that 6 by 1 less than 6. And then I multiply by 2 less than 6. And I would continue this like a sequence. Remember sequences in series in grade 11? Like a sequence of numbers that's always going to decrease by 1. So I can represent this as times ... and every factorial will get down to times 2 times 1. So if I had 10 factorial, I'd have 10 times 9 times 8 ... all the way down to times 2 times 1. And this can be used in a general notation, which we're going to use for factorials. Below here is just an explanation of what we were talking about with the number of options in each stage. But let's jump to the factorial notation. So if I was to talk about any number, let's call it n. n would be a natural number, a counting number. So anything above 0. So for example, 1, 2, 3, 4, 5, all the way to whatever you can come up with. So if I had a number factorial, it's really that number, n in this case, times 1 less than n, times another one less, so that's minus 2, n minus 2. And you could expand this as far as you really want to, but it will always end in times 2 times 1, like that. We're going to need that here later. But just so you know, there is a button on your calculator, which you should be aware of. And I'll just pull my calculator up. So if you go to the math button on the left column, so on the left side of your calculator is the math button. One of these things at the top, we've got PRB, which represents probability. And here, there's several things we're going to use, but for now, we're just talking about factorial. And number 4 is a factorial. Depending on your calculator, so I strongly suggest you try this on your own handheld. This one, I would need to type in the number first before I go to the factorial. So I would go 6, and then math, PRB, oops, and then number 4, and a factorial is put in, and I press enter. And so 6 factorial can just be represented by 720, like that. So pretty easy. So we're just going to practice this, and you can try this on your own. You don't really need me. So this one, type it in. You're going to get 40,320. When you get up to even just 23, you get massive numbers. And on your calculator, I put this one on on purpose. If I do this, PRB, I get this thing. And it's important to recognize what that is. What that E22 is means that you're times 10 to the exponent of 22. You should not be writing E because that's not formal math language. You should be writing like this, 2.59 times 10 to the exponent 22. I've chosen to round this because really once you get up to these giant numbers, right, like times 10 to the exponent 22 means you have 22 numbers after the 2 before you hit the decimal. So it's just a giant number. And so we're allowed kind of to round, I think, in this case, to 2 placements or 3 sig figs. The last one here, 0 factorial, is just a kind of a weird situation, but we need it to work out this way. And your calculator will work if you try it and press 0 factorial. It gives you 1. And we'll talk about this more in class, but you should know this. The simple explanation, well, it's not so simple, but quick explanation is that if you had no people and you wanted to arrange no people, technically there's one way to do that because not having an option to arrange them is an option. And we'll see practical examples where that comes up. And so this is somewhat needed. So let's play around a little bit with these factorials, and we're going to do some stuff where you actually are solving for variables with factorials and stuff, but we'll just use this one here. This one says simplify, but we're not going to evaluate it. What that means is that I'm not going to get a final answer that's one number. I'm just simply going to reduce this, kind of like I would reduce a fraction. So like, for example, if I started with 10 over 5, you would reduce this to just 2. In this scenario, remember a factorial is an actual mathematical process. So I can't just start crossing out factorials because it contains a bunch of other things. But what I can do is expand them. So 10 factorial is really this, and I'm going to write it out the whole thing, at least this time, but in the future I probably won't because it's a lot more work than is necessary. But 10 factorial is this, and if I write it over 5 factorial, maybe you can spot what's going to happen here. A bunch of stuff is going to divide out. So 10 factorial divided by 5 factorial, everything from the 5 factorial goes away. It's just divided out because they're common to the top and bottom. So you're left with 10 times 9 times 8 times 7 times 6. And because it says do not evaluate it, I'm just going to leave it like that. The next one, and you can always pause this video if I'm going too quick, just trying to keep it a bit shorter. 57 factorial over 54 factorial. I'm going to show it expanded, but obviously I'm not going to do all of the numbers here. I'm going to go to 54 And then I'm going to go times dot, dot, dot. And I know that this is going to go down 2 times 2 times 1. I stopped at the 54 because I took a look into the denominator and I saw that it's really just going to divide by 54 factorial, which is 54. And I'll show this as times 53 just to show that this is a sequence, times dot, 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 times 2 times 1. And ultimately what's going to happen is all of this cancels out. And so you're left with just 57 times 56 times 55. I think it's important to know that your calculator cannot do huge numbers, even up to 90, I think like 93 or something. If you type 93 factorial, your calculator will not work. It's just too big of a number. I think this one will work because it's actually a computer, so it can handle larger numbers, but your calculator won't. And so sometimes you do have to reduce things because your calculator can't do the number. So we're going to talk about a situation here and we're going to use factorials, but it kind of leads into what this whole unit is kind of themed around, which is permutations. So let me explain. This one says, how many ways can we line up any 5 students from everyone present in class today? So obviously we're not in class today. Let's say there's 16 people. So I'm going to say there's 16, just randomly, up at the front of the class. This is a slightly different situation than what we were talking about with lining up the blocks or 3 people at the front when you had 3 people. What's different here is that I have 16 people and I'm only going to choose 5 of them. So quite a few more options than if I just had 5 people and I'm going to use all 5. So I've got more items, or in this case people, than I actually want to use. So I've got 16 to choose from. There's a couple ways to think of it, and if we think about it the way we thought the last class's material, because I'm going to choose 5, it means that I've got 5 stages or 5 positions to line them up. And for the first person, I have 16 options, and then I put someone there, so it goes to 15, and it keeps going down like that. And they're all multiplied because this is the fundamental counting principle, like this. I could express this using factorials, and I want you to do this just to show you something. So this, and if you think about this, good to try to figure it out on your own, would be 16 factorial, obviously, but I have to divide it by something because I'm missing everything from 11 factorial down. So 11, 10, 9, all multiplied together, and so on. So I'm going to divide this by what's missing, which is 11 factorial. This is a situation which is a permutation. And a permutation is always when you have more items than what you're actually going to choose, but you want to figure out the number of ordered arrangements of it, or the number of possible outcomes. So I can represent this as 16p5. And so the 16 is the total number of items available. The P represents permutation. So this is permutation. This is my total number of items available, which is called N. And this guy, the 5, is called R. I'll put some quotations around these, which represents the number of items chosen. So the number of items chosen, in this case, we're only using 5 people, so that's the number of items chosen. If we wanted 8 people, we would change R to 8. And this is frequently used in situations like this. Just to note, the 16 and the 5 technically are like subscripts, so they're smaller than the P or down from the P, and it's slightly smaller. So below here is exactly what I just stated. This is an example of a permutation where you have a total number of n objects, but you only want to choose some of them R, and we're going to find out the number of ordered arrangements. So different than what we've been dealing with, although I think we had a question in the homework from last class that was about president and vice president. That technically was a permutation, we just didn't call it that. So sometimes you have the option, you could do things one way or the other, but when you start to get into bigger numbers, like let's say I had a group of 100 people and I wanted to choose 20 of them, I probably want to use the permutation because it's just quicker and less numbers I have to write down and type into my calculator. So I'm just going to write this out again. NPR actually has a formula, and you're going to need to know this formula. It's where you have n factorial divided by n minus r bracket factorial. And so it works out if I did that 16p5, n would be 16, so I have 16 factorial over 16 minus 5 bracket factorial, so I do the bracket first, and I'll just do this to the side. So I end up with 16 factorial over 11 factorial. Oops, there's my factorial, which is exactly the same thing we wrote there. So it works out the same. Not to confuse you, but often there are more than one way to express how this can be the notation for NPR. You'll also see it in the textbook like this, a P and then a bracket N comma R. It means the exact same thing, it's just different notation. Great. So here it says if I had P5 comma 3, what that means is that there are 5 items available, but I actually only want to use 3 of them in my arrangement. And we'll look at a bunch of examples where that comes up. So I'll just give that one as an example here. So P5 comma 3, that's really 5 factorial over 5 minus 3 bracket factorial, which comes out to 5 over 2 factorial. And you could do this on your calculator, or you could expand this, 5 factorial over 2 factorial, which comes out to 60, I believe. Or you could just jump to the answer. And so our calculator will do this for us. Again, I strongly recommend you try this because you need to know how your calculator will work. But if I go back to math and back to PRB, you'll see the second one down here is NPR. In this one, on this calculator, it allows me to get out of there. It allows me to type that, and then it prompts me to put the N in. So 5, I scroll to the right, and then I put the 3, and I press enter. It does everything for me. I don't have to worry about the factorials or anything. Some calculators, you have to put the N first. So you would have to put 5 and then go to math and NPR it. So example of where you would see this. This is like the classic data management question number 4 here. So suppose we have a group of 10 people and we want to choose the president, vice president, treasurer. How many ways can this happen? And so you've got more people than the number of positions. And so previously, which you can still do, it's really up to you, I would put 10 times 9 times 8. This is the same, really, as 10P3, 10 items. I'm going to choose 3 of them, and your calculator will give that to you like this. And so I think it's important to do it both ways or think about it both ways, because if you had 100 people and you wanted to choose 20, like I said earlier, you're not going to write out each position and go, 100 times 99 times 98 and so on. You're going to do 100p20, which is going to make it a lot quicker. So the next questions, I would like you to try them, but obviously I'm going to explain them. But I would pause the video, read through them. I expect you're going to get stuck on at least a couple of them. But it's good to really try this on your own. You've kind of got the understanding where you can figure this out potentially, but I think it's good to try it. So there's a mix of permutations and just factorial stuff in here and a little bit of other stuff mixed in. So pause if you want and give them a shot, and then watch the video if you need the explanation. So here's my explanation for this. How many arrangements are there for the letters Fermat's? This is 6 letters. They're all different. If they weren't, that would be a different kind of question. The first one says, how many arrangements are there if there are no restrictions and you use all the letters? So this is like 1, 2, 3, 4, 5, 6. I use all the letters, so it's really just like this. We're assuming you can't repeat them, so I can only use them once. So this is just 6 factorial. Probably, or maybe some people watching would think, could I use permutations here? You technically can. This would be the same as, you don't need to, and in fact, it's probably more work, but this is the same as 6 items, and I'm choosing all of them, 6p6. And if you type that in, it's the same as 6 factorial, and if you use the formula, you'll see it works out well for 6 factorial, which comes out to 720. So that one's pretty easy. The second one here, it says you use all the letters, but each arrangement must end in a vowel. So this is what I would call a restriction on the number of arrangements. And when you have a restriction, it's generally best to start your arrangements, figuring out your arrangements, by dealing with the restriction first. So I'm going to say always start with restriction. This time, I think it is good to write out all of the stages, or in this case, the letters. So there's 6. We're going to use all 6. So I get 6 stages or 6 places to put the letters. Starting with the restriction, the last letter must end in a vowel. So we're on all the same page. Obviously, E is a vowel and A. That means I have 2 options for the last letter. So I'm going to put the number of options, which we always want to do. It's the number of options in each stage. I have 2 options there. So the E or the A. That's the only restriction in this one. So you have to think, okay, well, I can't put both of them in there at the same time, but I put one of them in. And what that does is it drops my total number of letters remaining down to 5 for the 5 places. So I've got 5 options, let's say for the first. I put another letter there. That brings me down to 4. I put another letter there, 3, like this. So this could be simplified slightly into 5 factorial times 2, which gets me 240. Great. The next one says I'm only going to use 4 letters. And so it's like this. I have all 6, but I'm only going to line up 4. So you could do this 2 ways. 1, number of options here, 6, number of options for the next one, and like this. Or you could say 6p4 gets you the same thing, which is 360 different arrangements. Part D says you use only 5 letters, but the first letter must be a vowel, and it must end with a T. Oops. So I'm going to use 5 spots. What that means is that there's 1 letter that isn't used each time, but I can use I have the option of the 6, but I only can place 5 of them. So there'll always be 1 remaining. So I start with the restrictions. It really doesn't matter which one you start with in this case, but the T, there's only 1 T, so that means there's only 1 option at the end. That's the T. The must start with a vowel, so I have 2 options at the beginning. And so again, you think about this, you had 6 total letters to choose from. You put the T at the end, so that removes 1 letter, so you're down to 5. You put 1 vowel at the front, but you still have the other vowel remaining, so you're now down to 4. So this becomes 2 times 4 times 3 times 2 times 1, which again, you could put in factorials or just punch it in, you get 48. Good. Okay, the last one I'm sure most people probably didn't get, but if you did, that's amazing. This is a situation, it's like you have 2 items that must stick together through all of the arrangements. So it says if the letters R and M must be beside each other. So for example, I could have these letters of format. Let's say I have R, M, what's left? A, like this. Or you could have F, R, M, F, E, A, T, there's 6. Or another one, just to really be clear here, the E. But what I want you to see is that the R and the M are always moving together. Oops, not those 2. There we go. This, this, this. And so it's always moving together like that. In order to answer this or think about it to get the answer, I think it's easiest if you think of the R and M, because they're always together, instead of being 2 letters, it's like they've joined together and they become 1 letter. So when you have this 1, 2, 3, 4, 5, 6 spots, because the R and M are always together, it really kind of, in some ways, becomes 5 total letters instead of 6, because the R and M must stick together. And so what we can do is we go from 6 options down to 5 because we're treating the R and M together. The R and M can still move anywhere through, but they're doing it together. So instead of being 6 factorial, I get 5, 4, 3, 2, 1. And that takes care of most of the options. I'm just going to write below here, treat R and M as one letter. And so it's not quite the final answer. And this one, if you got this, that's amazing. But if you didn't, I wouldn't worry. Once you see it first time, it'll make sense. I could actually, instead of being R and M, I could switch them. And so I could have M and then R. So what that does is it doubles all of the number of arrangements. So I'm going to do a times 2 at the end. And this is the options for RM and the vice versa, MR, like that. So you end up with 5 factorial times 2, which we've seen this number before, becomes 240. That one's a bit tricky, but good to use, and you'll see some similar questions to that one in the homework. The homework for these questions, which is listed down here, we're going to do those in class. That's this day 2 stuff. But I want to show you some more factorial simplification and actually solving with factorials on the next page. And that's what I want you to work on for homework today. And so you're going to do these questions on the next page and plus this textbook question. So sometimes you get these expressions or even equations where you have factorials and you can simplify them to make things easier. So before we do this one, I just want to restate that if I have n factorial, it's really the same as n times n minus 1 times n minus 2, and that keeps going until I get to times 2 times 1. And whatever the thing is in front of the factorial, in this case n, you always start with that one. So in order to simplify these, I'm going to expand the factorials. So if I have n plus 2 all factorial, the first number or term will be n plus 2. That's the thing that's having the factorial. The next term, hopefully you can guess at this, will be 1 less than that. So n plus 2 minus 1 becomes n plus 1. The next term will be 1 less than that, which just simply becomes n plus 0 or n. And then it starts to go down like this. And I'm going to end that expansion there. And you'll see why in a second. You could keep going. It's not wrong to keep going, but I'm just going to stop there. The reason I stop there is because I notice this is really just in the denominator. And when you get more familiar with this, you'll know, okay, if it's n factorial, it just starts with n, and then it goes n minus 1, and then it would be n minus 2, dot, 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 times 2 times 1. So you will see quickly here, there's a lot of stuff in the top and bottom that's the same. So n can go away. In fact, everything below n just simply divides out. And so I'm left with this expression, n plus 2 times n plus 1. And I'm going to leave it in this factored form. It's not wrong to expand it, but I'm going to leave that there. So that's my simplified expression, no longer any factorials. So obviously quite a bit simpler. Similar to the next one, we're going to go beyond actually simplifying it. We're actually going to solve for a variable. So it says solve for n, and you'll always see this, that n must be a natural number. It just means it's going to be above 0. So I've got the left side of the equation, 2n factorial. So I'm going to start with 2n. The next term will be 1 less than that. 2n minus 1. The next term will be 1 less than that, so 2n minus 2. And it's always good to glance in the denominator. 2n minus 2, oh, I just wrote that in the top. That's going to be the same in the bottom. I'll go one more, 2n minus 3, and then times dot, 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 times 2 times 1. And then the denominator will be that, 2n minus 2, 1 less than that, 2n minus 3, times dot, 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 times 2 times 1. So in the end, all of this is going to divide like this. And I'll write the right side of the equation here. This is 18n. So let's just rewrite it with all those things that have divided out. And so I've got 2n times 2n minus 1 is equal to 18n. So we've now got an equation that you would have seen this in grade 10, where it's really ultimately quadratic. And in order to solve for the variable, first thing I have to do is expand or distribute the 2n in. So let's do that. So this becomes 4n squared minus 2n, and then equal to 18n. And in order to solve, I must move the 18. I got to move everything over to one side. So I'm going to move the 18n over. So that becomes minus 2n minus 18n, which is minus 20n. It's equal to 0. And then I've got a quadratic, so I need to factor in order to solve this. Look for a common factor, I think, first. So 4n I can pull out. That leaves n minus 5. That's all equal to 0. So ultimately, this would be a factor of n equals 0, and this would be n equals positive 5. The 0 doesn't work in this scenario, and if you imagined it, the reason because if I had 2n minus 2 and I subbed in 0 factorial here, if I subbed in 0 for n, I'd end up with minus 2 factorial. That doesn't make any sense. I can't have a negative factorial. So I can't use that one, so my answer here is n minus 5, or n equals 5 rather. Great. So try those practice questions on the next page, and then there are solutions in the content library, and then give the last one here from page 81, 16a a shot. And again, we'll do the day 2 stuff together in class. Okay, let me know if you have any questions. Take care. Bye.